So sure, while we're waiting, why don't you introduce yourself?
Yeah, hi. Um, well, I mean, firstly, Richard, thank you for inviting me. Actually, it's quite, it's not something I've done before. I've never been to one of these, so
Awesome.
it's quite interesting. I wish I could have joined earlier or joined in person, but next time.
Next
Um,
time you're always
yeah. So, for everyone, my name is Naushir Patuck, and I work at Raspberry Pi Limited, so not the foundation. So we're the ones that design the boards, write all the software, things like that. And For the most part, I specialize in imaging and multimedia. So things like the camera systems, the video encoder, displays, things like that. And more recently, I started getting involved in the AI machine learning area for some of our products. Now, I'm not an AI engineer. I'm not an AI expert by any means. So I'm still learning as well. So hopefully I'll be able to answer any questions you guys have. But if not, I may have to come back to you if it's a kind of very specific on AI.
all right. So what do you do for fun? Do you build stuff with Raspberry Pis, or you just make them work?
I make them work. I like building clocks in my spare time.
Ah,
So things like Nixie clocks,
oh,
split flip
nice.
clocks, things like that. I don't know why. I've just got an obsession with that. It's probably my engineering background.
Yeah, yeah. I think a clock is a. I think every Raspberry Pi enthusiast should build some clocks. I've
Yeah.
built a couple of them. So yeah, I really like building clocks. I don't know what it is about them.
No, I don't know. I mean, it just kind of appeals to the engineer in me, I guess.
Yeah, one thing I wanted to build was a water clock. Have you ever seen a water
I
clock?
have seen one actually. Yes, yeah. I
I
have
saw
seen.
one in China where they measure the passage of time by changing the flow of it from
Yeah,
different bits and things like that. That was pretty cool.
very cool stuff. Yeah. I want to build a kind of one of these piezo-magnetic clocks, which actually kind of display digits with liquid, which is magnetic,
Oh yeah,
ferromagnetic. So, but it's not very reliable. So
yeah,
one
that'd be
day.
pretty cool though.
Yeah, yeah, no.
Yeah,
So I've seen people do these kind of builds, and yeah, it looks really nice. It doesn't last very long though.
right. Yeah, it's all good fun though.
Yeah,
Well, I think we're ready to start. So let me see. I think we're stable. I don't think anyone's waiting in the waiting room. So yeah, if you want to get started, whatever, ready.
sure. Okay, so right. Okay, so Raspberry Pi, about 5 weeks ago, early June, we released one of our newest products, which is the AI kit, as you can see in the slide. Um, the AI kit, we collaborated with a company called Halo on this product. Now they make AI accelerator modules, high performance, edge-based modules, also modules that you can connect to your PC. Obviously, we've chosen one of the edge modules to work with. It's available for $70, I believe, which is quite cheap given the capabilities you get. So what does the kit contain? It's basically one of the standard M2 hats that we supply, along with the Halo AI accelerator module. So here you've got the M2 hat. Here you got the Halo accelerator module. Plug this in over here, and you connect the FPC cable directly into the Raspberry Pi 5. And this is the PCI Express interface. The M2 card, we run it at PCI in PCI Gen 3 mode, single lane operation. Normally, we recommend PCI Gen 1 for most devices connected to the M2 card, simply because we haven't qualified everything for Gen 3. However, we have qualified the Halo module in the AI kit for Gen 3. So if you're running it, switch to Gen 3 mode, it'll give you quite a big performance boost. All of that is documented though, in our getting started guide, which I'll kind of briefly touch on as well at some point. So what are the key features? So, I mean, the headline feature is this 13 TOPS of inferencing performance. So that TOPS is tera operations per second. It's basically a measure of how much compute can you do on this thing. It's not, like everything, it's not easy to compare a TOPS number between different vendors, but we do our best. And just for an example, the Google Coral device, which is kind of probably the most popular edge AI accelerator, runs at about 4 TOPS. So this thing is quite a bit more performant than that. As I said, we run it in single lane PCIe 3 mode, and that gives us a throughput of around 8 gigabits per second. One of the kind of biggest things that we wanted to try and do with this device is introduce kind of an AI accelerator, which is easy to use. So we've spent a lot of time integrating the software and the kind of runtime hardware into our operating system. So kernel drivers, integrating with our camera stack, these kind of things. We've done a lot of work on that. And hopefully that means it's going to be really easy for a user to just pick this thing up, run a few commands, and get it up and running. And because of the integration we've done, it's compatible with any camera that we provide or any third-party camera that's integrated into our camera system. The hardware itself is extremely capable. Besides the kind of 13 TOPS of performance, you can kind of time schedule the hardware to run multiple neural networks with a single camera. So you can run many, many models on a single frame coming from a camera. Or you can run the multiple neural networks on different camera feeds at the same time. So Raspberry Pi has 2 camera ports, and you can run 2 cameras simultaneously on it. With the AI kit, you can actually run inferencing on each of those cameras separately. Obviously, you share the kind of performance through and memory throughput for the single device, but for the most part, you're probably not going to run into any problems. Yeah, and as I emphasized again, the biggest thing we want to kind of talk about is the integration with the Raspberry Pi imaging stack and the whole operating system. So I'll talk a bit about models. So neural network models are things that run inferencing and generate output, right? Inside these models basically describe a whole bunch of operations where you take an image in, you perform millions and trillions of operations to get an output. And now that output depends on what your model is trying to do. So for example, an image classifier model will take an image and try and classify it into something like an indoor environment, outdoor environment, a beach, a mountain, snow, things like that. That's a classifier. You've got image inference, so where it identifies objects in an image. So things like people, cars, bicycles, animals, phones, watches, computers, whatever the model has been trained on. And you got many, many different classes of models. So Halo have provided a model zoo, which is a place, a resource where you can get a whole bunch of models that they've compiled, ready to run on the Halo device in the AI kit. Now, it's very extensive. So any kind of model you're looking for, chances are you'll find it in the model zoo. So they have that hosted on GitHub, as you can see over here. Here's the kind of categories of models that they have. And within each category, they have many, many, many different models using different network architectures. So for example, here we've got like the pose estimation models. We've got center pose, YOLO, and a few others underneath. Instance segmentation, this segments the image into different objects, as I mentioned earlier. So again, you've got many different models. And the third one, as an example, object detection. Again, you've got many different models that are compiled and optimized to run on the AI kit. Now, what are the difference between these models in object detection? Each model over here uses a different architecture to generate your final result. The difference is generally how fast they run, how capable they are, and how many objects they detect, for example. So depending on your use case, you can have some kind of compromise. If you're only interested in people, you can run a very specialized model that only detects people, or maybe only detects animals or something like that. I'll talk a bit more about that later because you can kind of tune the model, pre-existing models, to do exactly what you want as well. So the Model Zoo is an open source, an open resource where you can just pull the models and run on the AI accelerator. Now, so the software. I've talked a bit about what we wanted to do with the software to make it as easy as possible. And here's our getting started page for the product. And I'm not going to go through it, but essentially, that's all you want to do. So update all your software and then do sudo apt install halo all. That pulls in all of the libraries and all of the additional resources that are needed to get the Halo device working. So that's it. I mean, that's our goal. Our goal is just to make things as easy as possible. And hopefully those 3 commands are easy enough. Once that's done, you reboot and you got your Halo accelerator ready to use. So as I said, we've made some demos. Unfortunately, it'd be really nice to kind of get one of these boards live running in front of you, but we can't do that because I'm remote. So we've made some demos, and here's one of the kind of object detection demo. Just let me know if you can't see the video when I press play. Yeah, great. Okay, so this is an object detection demo running at 30 frames a second on the Raspberry Pi. It's recording a video and it's pointed out outside our office, actually. This is the A14, and it's just picking up all of the cars and trucks as they go along. And it even distinguishes between cars and trucks, and they're going quite fast. There you go again. So we have in our demos, we've chosen a few of the models from the Model Zoo. So we've chosen YOLO V5, V6, V8, and YOLO X. YOLO is a kind of neural network model architecture. It stands for you only look once. It means it takes one pass of the image to generate the inference output. It doesn't do it over and over again, and it doesn't use history from previous frames. So it's like a one-shot operation. Oh, sorry. So there's another one is pose estimation. So this is in our office. You can see as people walk up and down, it detects the pose and just draws the key points and the skeleton on well, that's me, and that's my colleague James coming past. And again, this is running at 30 frames a second, and we're just recording the video through our camera application. So the third one is what we call subject or instance segmentation. So here we've got a normal viewfinder, and here we've got what the model has done. It's basically masked out different objects live while the viewfinder is running. So you've got like me over here, and you can see I've been masked green. The plant here has been masked orange, and then there's a few other bits and pieces, like the screen has also been masked. So these are just some of the examples we've added, and Halo have many, many more. So you get an idea of what you can do with this thing. And all of the kind of real heavy processing is handled by the Halo device itself. All we're doing on the Raspberry Pi is feeding it frames from the camera. And then we're taking the output of the neural network. And for example, in this case, we're just drawing over the picture just to show where the objects are. So let me talk a bit more about the software, and let me start talking about the camera software specifically. So I don't know how familiar everyone is with the Raspberry Pi camera stack. We use something called libcamera. We follow the libcamera API, and we're actually quite a big contributor. I think probably the biggest contributor to libcamera outside of the kind of core development team. So libcamera is basically an API for advanced camera use on Linux. All of our cameras, so we Raspberry Pi sell kind of the camera V1, V2, V3, HQ cam, GS cam, all of them work through libcamera. It's quite a capable and powerful stack. And on top of that, we've created an application framework called RPiCam Apps, which talks to libcamera and we have like kind of a suite of applications which takes, for example, still image captures, or it does video encode, or it does all sorts of kind of things that you'd expect to use with the camera system. Or you can kind of use one of the applications to record a video and stream it over the network, things like that. So RPiCam Apps is the kind of application framework I'm talking about. It uses the libcamera API. The libcamera API drives the actual physical camera module, and it drives the ISP. Now, the ISP is a hardware block that takes images from the sensor and processes them to make them visually appealing. It does a lot of work, and it's an extremely complicated block. Raspberry Pi we have our own in-house designed ISP on Raspberry Pi 5. Specs are available, and all of the drivers and everything are all open source if anyone wants to have a look. But that's a kind of hours of like detail there, which I won't go through. But so the ISP basically processes the images coming directly from the sensor and generates, for example, two outputs. One is a YUV output. Now, YUV is just an image format, but it's a specific image format that's used for video encode or JPEG encode and things like that. It can generate a second output, which is just a standard RGB that pretty much everyone knows, right? That comes out of libcamera. libcamera handles all of the kind of configuration of the ISP, configuration of the sensor, the data flow of frame buffers going from the camera to the ISP and out. Then RPiCam Apps takes over, and it runs a post-processing stage. So we have multiple software stages that can run in this post-processing framework of RPiCam Apps. And they can take these images and do whatever they want. So analysis, they can paint over the images if they want, or whatever they want, and you run it in a chain. And after those post-processing stages have completed, you go to the consumer. So the consumer in this case can be a viewfinder, it can be a RTSP stream, it can be a video encoder which encodes a file on the file system, or it can be a JPEG encode, whatever you choose. So what we do now is one of these software stages will call the Halo device to run an inferencing neural network model on it and generate some output. So that's how it works. And as you can see, if you run multiple of these, you can actually run multiple neural networks on a single image. Now, why do we have two images here? Generally, a neural network doesn't take a big image in to process. It takes a much smaller image than what you produce for a viewfinder. So output 0, this YUV image, is typically something like 1080p wide, which is going straight to your viewfinder or going straight to the video encoder. output 1 will typically be a much, much, much smaller image, which will be the size that the neural network model accepts. So generally, it'll be something closer to VGA. And it'll be in RGB format because neural networks are generally trained on RGB VGA size images, for example. So the input to the neural network must be, or generally should be, the same size and format that it was trained on. And that's network dependent. So I've got some code here. I'm just going to go through it very, very quickly. So this is the interface to these post-processing stages. This is what it looks like. We run in C++, really. So we've got this kind of post-processing stage base class. And we've got a Halo post-processing stage, which is kind of a derived class. This is a generic stage, but it needs to be further subclassed for specific neural networks, which I'll show you later. So this constructor reads some parameters on how the stage must operate, configures the stage to tell it these are the inputs that you're going to receive. So the YUV input, the size of the YUV input, the RGB input, the size of the RGB input. Ready with this is just kind of our Raspberry Pi's abstraction, just to say, is everything ready? If we want to do some post-processing, dispatch job, basically, this is the thing that says, dispatch the job to a Halo. And here's your input. Here's a job pointer, and this is the output. Now, neural network terminology calls the output of a neural network a tensor. So a tensor, the format of a tensor and the size of a tensor is dependent on what the neural network does. So there's no structure to it. It's entirely dependent on what the neural network is going to generate from the input. We've got an allocator class because Halo requires specific constraints on the frame, on the input tensor and the output tensor, how it's padded, how it's allocated. So you have to allocate an output tensor for the output of the Halo device, and you've got to take the input tensor, which is the image that we generate from the ISP. So here's this YOLO interface. So this is one of the examples I showed you earlier. It does basic object detection. So again, we've got the read, we've got the configure, and we've got the process. Process is where everything happens. So on every frame that gets generated from libcamera, we call process. And we pass in this completed request pointer, we pass in the frame buffers that have been generated by the ISP. And the process then goes and kicks off the Halo device to say, return me some objects that you've detected, you can detect from this frame. And then we paint it on the viewfinder frame, on the big viewfinder frame. Again, here's an example of how we configure these software stages. So YOLO inference, the HEF file, this points to the neural network model file that we want to use for this software stage. And here are some parameters that we have for this specific example. We only allow 20 objects to be detected at most. Objects that are below this threshold don't count or don't get sent to the results. Meaning if it's like kind of under 40% accurate, if it's under 40% confident that this is an object that it knows about, it will just drop it. And we do some temporal filtering over here to just kind of smooth out the bounding boxes as they move across frames. Because the neural networks don't do that. The neural networks only look at one frame at a time. This is all optional anyway. So how we've designed this system is that this does the object inference, and then it writes the results out into a metadata file, metadata block. We've got another software post-processing stage running that actually takes that metadata and draws boxes over it. So we've got two software stages running, one doing the inference with Halo, generating results, and one drawing those results on the big viewfinder frame. Now, what that allows us to do is kind of abstract out the bounding box drawing code from everything else. So in these stages that I talked about earlier, what we also have is a TensorFlow-like post-processing stage, which can run neural networks entirely in software. And you can compare how fast they run on a Raspberry Pi 5 purely on the CPU versus the Halo device. So an example, one of these neural networks that does object detection generally runs at about 1 or 2 frames per second on the CPU. And the Raspberry Pi 5 is quite a beefy CPU. Versus on the Halo, it'll run at 60, 90 frames per second. So it's quite a significant difference. So that's our PyCam apps. One of the other camera interfaces that we have, and it's really actually probably more popular than our PyCam apps, is our PyCamera 2 interface. For those who don't know, it's a purely Python interface into libcamera. And it's extremely powerful and it's extremely easy to use. And one of the things you can do is you can actually kind of use Python in an interactive session while the camera's running. So your camera's running in the background in your Python process, and you can just kind of periodically ask, give me a frame, or tell me what's happening now, or change some parameters live. It's almost trivial to do in Python. But anyway, this is a Python script running PyCamera 2 that effectively does the object inference exactly like we saw in the C++. So we configure PyCamera 2 for two images. So a big image, which is going to go to the viewfinder, a low-res image, which is the thing that's going to go into the Halo inferencing engine. We start the preview, we start the camera, and then that's it. So for every frame that comes out, we take the low-res image and we pass it into the Halo inferencing engine. And that's pretty much it. And then we extract the output from the Halo device and draw bounding boxes on it. So it's actually that simple, and that's all you need. Now, I've got this code over here, but actually we don't have PyCamera 2 and Halo integration available just yet. That's going to be coming to our next release. So more on that later. I talked earlier about the model zoo, and they have tons and tons and tons of models there. But if you did have a very specific use case and you couldn't find a model in the model zoo, Halo have what's called their data flow compiler tool available. Now, this compiler will allow you to do one of two things. So it works in bring your own data mode. So what you can do is you can take an existing neural network model and what we call retrain it on specific images that you are interested in, or specific objects that train it on specific objects that you're interested in if you have a specific use case. So it's a fairly small operation. You just gather a bunch of images, you take the neural network model, throw it all into this data flow compiler, hit the go button. It'll take a while to retrain, and you'll get a new model out, which will then be trained on your additional images. The other mode of operation is bring your own model. This is a bit more complex, and you probably need to be fairly well versed with how models work and things. But this is saying, I've got a model that just does not exist in the model framework, or nothing close exists, and I want to get this model running on the Halo device. So in this mode, you're going through many, many steps to try and convert the model. And specifically what you're doing is you're quantizing it. You're making it a bit smaller so that it will run on the Halo device. But again, it's a lot more complicated than just the bring your own data way. This is something that we've not actually explored much ourselves at Raspberry Pi, but when we get a chance, we will start looking at this and how it works and probably write some tutorials and things. So, as I said, what's next then for us on the AI kit? I mentioned Python PyCamera 2. I've given you an example there, but it's not actually available yet because the Python bindings aren't officially supported by Halo yet. But actually, having said that, I have been given word that this week, just this week, that they are available in the next release, which is coming up soon. So once we package them up, we're going to kind of release that package. We're going to release the examples for PyCamera 2. Independent crop control. So right now, let me just scroll back a bit. Right now, as I mentioned, we get two outputs from the ISP. They have the same field of view that the sensor generates. But that's just an artificial limitation. What you might want to do is you might want to have completely different fields of views for the image that you're going to send to the viewfinder and the image that your inference is going to run on. There may be use cases. I'm not entirely sure what, but the hardware supports it. So we just need to bake that into our software. As I mentioned, data flow compilers is something that we're quite interested in. It'll be nice for us to kind of go through, understand what's going on, how we do things in both modes, try some examples for ourselves, and maybe write some tutorials. So that's something we're going to do. And then anything else. So as I said, this is quite a new product. It's the first AI-based product we've ever done. So we're looking for community feedback to try and understand what people will use this for, what things are missing, what things we should work on, what demos people want to see, what tutorials they want to see. So yeah, I mean, we're quite excited, and yeah, it's been interesting and quite a learning experience for us as well. So, and yeah, I think that's about all I had to kind of talk about. Is there any questions that I can answer now or talk about? Maybe explain a bit more.
There's a bunch of questions in the chat, but I did have a question. So this, about 6 months ago or something like that, maybe a year ago even, you introduced the global shutter camera.
Yes.
And at the time, it said this sort of camera is really good for AI purposes because it's got lower resolution and it's global shutter, so you don't get like the tearing of images, things like that.
Oh, hello?
So the question is, like, how does that have you integrated with the global shutter camera, and how's that working?
Oh, sorry. I either I got cut out or you got cut out. Sorry, I missed the question.
Okay.
I heard.
So let me finish that question then. So the global shutter camera,
Yeah.
because it was mentioned that it was really good for AI inferencing.
Yes, that's
So how does it work in reality? Is it
so.
have you used it, and is
Yeah.
it working really well? Is it?
It does. Okay, so the advantage of global shutter camera, the advantage of using a global shutter camera for these kind of applications is that you expose the whole frame at once, which means that you don't get these kind of rolling shutter effects with the other sensors, meaning your image is not distorted in any way. Especially, I mean, rolling shutter cameras can distort the image if you've got fast moving objects or high motion or high movement anywhere, because they're kind of exposing down the frame. So the global shutter camera gives you kind of a proper snapshot, which is undistorted. And neural network models generally are trained on these kind of images. From the global shutter camera is always going to be better than a rolling shutter camera for fast moving objects or fast moving scenes. So that's the advantage there.
So it might work with F1 cars rather than just normal cars.
Yeah, yeah. I mean, you know that car example that the video that I had earlier. Actually, that was a rolling shutter camera, to be honest. So it worked quite well.
Oh, so I did put a long question in from a friend of ours.
Yeah, yeah.
He's in Australia, so he didn't think he wanted to wake up quite at 3 a.m. or whatever it was his time. So what he's asking is he's got one of the AI kits and he's working with it, and he isn't quite sure which model in the zoo to use.
Okay.
So his use case is that he has people building these kits to charge batteries, like if you're out camping or whatever. So it's sort of a battery charger. So in his company, they sort of collect grab parts from bins and stuff like that. And he wants to make sure that they're grabbing from the right bin for the particular variant of the model of the product they're building. So I guess his question was, how do you choose which model in the zoo to actually
I mean,
use?
to be honest, one of the kind of simplest things I do is go and write this question on Halo's community forums. And yeah, because again, like kind of my AI knowledge is fairly limited. And there's a large number of models. So I would suggest go speak to send a message on what they call the Halo Developer Zone, which is just a forums, and they'll jump at it. They'll tell you exactly what you need.
Very cool. So he has offered to do a presentation at some point
Lovely.
when
Yeah.
Australian
But I mean,
time.
yeah, I mean, we're more than happy to kind of have a chat with him ourselves as well to kind of see what his use case is. Because again, this is a brand new product for us. So, we're really keen to see how it's going to be used and what the kind of hard bits are.
Yeah, so I'll tell him to drop you a line, actually.
Yeah, absolutely.
He's very
Yeah.
keen. He does a lot of stuff. So I think Raspberry Pi would be quite interested to hear about all the stuff that he's doing.
Yeah.
I mean, question from Francesco. He's asking, how does it compare to the Jetson Nano? I guess this is the Halo.
Okay, so I think Jetson Nano is kind of a big family of products, isn't it? So they have products which are kind of the low end of the scale, which I think are going to be like, again, don't quote me because I'm not sure, but I think they're kind of 4 to 6 tops. But then you've got the very, very bigger 20 tops or so, 20, 25 tops even. Now the Halo 8L device that we have on that we have in the AI kit is rated at, is kind of rated at 13 tops. Halo also have a Halo 8 device, which is effectively twice that performance. So that's going to be 26 tops, which is probably more in line with the kind of newer generation Jetson Nano devices. That part, I mean, it's not part of the AI kit, but it will slot in exactly the same and run exactly the same software.
Wow.
It'll just give you more performance.
So have you sold lots of these? Like, what are the sales like?
We don't sell the 8 device. I mean, we only sell the kind of 8L.
Yeah, no, the Halo though. Like, how many have you guys sold?
Oh, I think I've lost you again.
Yeah. So the question is how many have you guys been selling well, these new hats?
It's been selling really well. It's been selling really well. I think the initial batch sold out straight away. And we've got kind of more on the back order ourselves. So no, it's good. I think people, I mean, I hope people kind of take the same view as we have and to show that we're trying to make AI easy, if you see what I mean.
Yeah.
We're trying to get people running as fast as possible. I mean, before this, if you asked me to kind of write an AI application using a camera feed, I wouldn't even know where to start. I wouldn't even know where to start. So, and I'm sure other people have the same view. And I design camera systems. So, like having like kind of 100-line Python example to kind of take camera feed and put it through like a very capable AI accelerator, I think is a big win. So I think people recognize that.
Yeah. So Nick asks the question, 30 frames per second is understandable, but what is the delay? Like, why can't you go faster?
You can. There's nothing stopping us. We generally run our cameras at 30 frames a second because that's convention.
Yeah.
But the inferencing can run faster. Some of the models can run 60, 120 frames a second, even faster. As always, there's a trade-off. So some of the more accurate models will be slower. The YOLO V8 is probably the most accurate model that we have, I think. And that can probably run something like 60 to 80 frames a second.
Impressive.
You're actually limited by the sensor itself, which cannot do more than generally 60 frames a second at a certain size.
Okay. Yeah. And then it's asked whether or not you can recognize a person by their gait, like how they walk.
Yes, you can. Yes, you can with the pose estimation. You can definitely do things like that. Yeah.
Yeah.
And as I said, you can do things like recognize a person with the gait analysis, and then kind of switch over to do kind of facial recognition or something, if you will, if you want to do that as well. So run multiple models on the same image.
Oh, right. Yeah. Yeah. I thought that was very cool. I thought it was a very
Yeah.
interesting idea that you're sort of running these things and they run in parallel, I guess, do they?
So one of the examples, one of the kind of more common examples is card license plate detection. So you first run a neural network to detect the car, then you kind of crop the bit of the image that has the license plate, and then do license plate recognition on the same image. That's a typical use case actually for something like this.
Oh, nice.
For models.
So Greg is asking why is the distinction made between RGB and YUV for the CAM processing?
So RGB is we typically use RGB for neural network processing because the models have been trained on RGB images. That's the only reason. YUV is more common for kind of video encodes, still image encode standards and things like that. There's no reason why we can't use RGB on both of them, like both images. Typically, if you cannot send an RGB image to a video encoder or a JPEG encoder, you have to do the conversion to YUV before you send it there.
Okay.
But if you're just running a viewfinder, you can have both images RGB. That's no problem.
And do you ever want to like change to black and white to improve things, or is that something that's not needed? Or
it's possible. It's possible. Again, depends on how the neural network has been trained.
yeah.
So if you train a network on monochrome images, that's what it'll work best with.
Right. Okay. And Nick asks, can it run models from the Hugging Face? I don't know what Hugging Face is.
Unfortunately, I don't know what Hugging Face is. So, can you elaborate on that? Like, I'm really not sure.
Or Nick, do you want to unmute your mic and say the question directly? I'm not sure what the Hugging Face is. Nick, you there? I assume you can unmute yourself.
Just put a reply to your message. He says it's GitHub for LMM.
Oh, it's GitHub for LLM. Okay. Yeah, I guess.
I'll have to kind of defer that question to Halo. I'm not sure, to be honest.
Yes, it
Yeah,
should.
Hugging Face hosts a lot of models, and they have different sizes. So from super small, like Tiny Llama, for 300 million parameters, to huge one with billions and billions.
Okay. It might be. It might be. I am not 100% sure on that, to be honest. It's worth kind of again going to the Halo developer zone and asking them. I know they have plans for models like Whisper and a few other kind of the smaller LLMs to run on the 8L device. So that's something that will be coming soon as well. So it could be that one of these kind of model families will work. Yes.
Okay. So Nick also asks whether the Halo 8, the 26 teraflop one, will work with the Raspberry Pi 5.
Yep.
It's also an M2.
Yep. It will fit in exactly the same slot, run exactly the same software that we run right now. You'll just get more inferencing capability.
So Sean asks, can you run multiple models, motion detection model, and then triggers an object detection model?
Yeah.
So it's a
Yeah,
question.
yeah, that's what we talked about earlier. So yeah, you can run multiple models in sequence, and effectively they are parallelized when running.
Right. And you can run them in serial as well, can you?
Yes, you
So
can.
I guess.
Yeah.
Okay.
You don't want to run it in serial because it's less efficient. You want to let the kind of software deal with the scheduling of the hardware with kind of
Okay.
multiple models with across multiple frames and that kind of stuff.
Yeah.
It's a lot more efficient that way.
Okay.
Because
And
what you
the,
could do is you could kind of let's say you have sorry.
yeah, go ahead. Sorry.
Yeah, so I was going to say, let's say you have multiple models running on kind of multiple frames. You don't want to kind of switch models and context switch now. You can run one model on multiple frames, next model on the multiple frames. Like it'll try to do the most efficient thing.
Sorry, very cool. So Andy also asked, can it be used to accelerate training a model from scratch, or should that be done elsewhere?
So this is the generally speaking, retraining models is a time-consuming process, and you kind of go through a lot of heavy computations. So it's best run on kind of PC, a big environment with a big graphics card to do the retraining.
Okay.
So it doesn't necessarily accelerate the retraining step.
So I guess at this point, it's pretty new to the community. So I don't have you gotten any like really cool projects back, or it's still so new that you haven't seen a lot of stuff that people have developed?
So people have made use of the Halo device with a Raspberry Pi CM4 module. So this is kind of outside of the AI kit, but using exactly the same hardware. They've made a product which is a smart cycle backlight. So it's a light with a little camera and a Halo module that detects cars coming from the back, and it'll kind of shine brightly to kind of warn the cars that there's a cyclist here, something like that. So that's actually a product that's already out.
Yeah, I did see a product my wife wants is a cat flap that detects when the cat's
Yeah.
got a souvenir for us, not carrying a mouse or something.
Yeah. That's actually quite a common ask.
So getting pretty sick of finding squirrels and pigeons and rats and stuff in our house. So
Yeah.
So apparently there's a product that does that, but I just have no idea if it's actually a proper product or not. But it sounds like something could be possible.
Yeah, absolutely. Yeah.